Okay. First of all, thanks, organizer, for giving this slot to present the work which we are doing. So I'm Chayan from India, Ayuka, working as a postdoctoral fellow. So I'll be talking about deep field imaging using one UV imaging telescope, which we are doing like in a collaboration with other people, which are listed here. Now, so we have fairly a small group at Ayuka working in the deep fields led by Kanak. And we have two postdocs working here, myself and Sauradev, who was here earlier, and 5 PhD students. So there are many topics we are trying to explore using the UV imaging of the deep fields, like reionization by identifying the Lyman continuum leakers, then evolution of dust extinction in galaxies, luminosity function, selective clumpy galaxies in the nearby redshift, and then blue compact dwarfs, XUV disk, and many things. But I'll be mainly talking about the part which I am leading in this whole collaboration. So just to define the deep field, like when you see a patch of sky where there is no galactic stars, for a small amount of time, you see this type of objects where mostly the bright sources you can pick up and clearly see. So this is the image of Hubble deep field just from the Aladdin. Like if I take the Pan-STAR patch, which is shown here, but the same image seen in Hubble is like with 11.3 days of continuous like exposure time. So you see extraordinary things, and we know like how deep fields are started. So with this idea, like the deep fields are mainly proposed using the HST observation, and the idea was to image the whole time scale of the universe, like starting from the very beginning, the highest redshift galaxies to the present day. You get them everything in the same patch of the sky, and then you can try to study the evolution of the galaxy and different properties with time. Now, as HST started, we know that there are many deep fields already proposed and observed. We have the highest quality image from different instruments. Now, these are the like deep fields we know. Now, we targeted few of these deep fields using the instrument we are using. So just to briefly say about the instrument we used for that, so this UV-80 telescope is onboard AstroSat observatory, India's first multi-wavelength observatory launched in 2015. And this is the telescope which observes in ultraviolet and near UV and the far UV telescope you can see here. So these are the filter systems installed in the telescope. We have multiple filters in the far UV channel and near UV channel, starting from like wide band, and then you have medium band, narrow band filters. So it can simultaneously observe in the FUV and near UV channel with multiple filter options, and you can see the angular resolution is 1.2 arcsecond somewhere. So this is a comparison image of UV-80 and GALEX of a star forming region imaged by both the telescope, and you can see the difference here. So we have been using this telescope to image some of the HST deep fields, which I just showed. And the idea was started at 2018 with the two deep fields, good south and north. And we are using this mainly these three filters, one in the far UV and two in the near UV. So later on at 2021, we further proposed for other 4 deep fields like 2 Hubble frontier clusters and NEP edges. And the last year we proposed for this Hubble cluster, lensing cluster. So mainly I will be talking about this field, AUDFN, which is the GOATS North field, which I'm leading. So these are the kind of deep field image we got from UV-80 imaging. This is a GOATS South field and the GOATS North field. The other fields are like we are having the we have completed some of the observation. We will be processing the images. So these are the other fields and their field of view in the UV-80. Now, what advantage we have when we are imaging with UV-80, and because we already have galaxy images for the UV bands, what specific advantage we have? So if you see this image, like as I said, 1.2 arcsecond, you can see the UV-80 and galaxy difference. And here the HST images, which is like the best resolution we have in the UV. If you compare, you can see like we we have a better sensitivity in the sense for the very faint source, we can pick the source which is lost in the galaxy image. Now, apart from that, like this is the Goods North UV-AT image, color composite far UV and near UV. If I just show the few of the sources detected in the imaging, you see like we go up to 25 magnitude and redshift one is sources, and even fainter sources at very high redshift. So we go very high resolution compared to the galaxy and better sensitivity to avoid the deep blending issue better. Now I'll be mainly focusing on Goods North part and whatever work we are doing. First, producing the photometric catalog, and then that catalog combined with other ancillary data in the archive, use them to produce some science aspects which we already had in the proposal time. And there are some other works which I'll not be talking about, which is like done by some other members in the group, like the UV luminosity function and leakers in the intermediate redshift range. So first of all, to produce the deep image, we use C3 Lab software, which is customized for this UV-AT telescope. There are certain things we correct, like these are mostly for the space-based data. When you have the raw data and you want to produce the science-ready product, you have to go through all these corrections. So this software is customized for doing all these corrections. We step by step perform everything. So 3 points I just want to highlight here. So for deep fields, it's very essential to retain the good PSF when you're combining multiple frames and producing the deep mosaic. We do the astrometry carefully using Gaia, and also the background. So every photon in UV is very expensive, and we take care to say what is background and what is actually signal. So there are multiple things done for constraining the background and subtracting it while doing the SNR calculation or photometry. Yeah, so for the first part, we took the Goods North image, and then, as I said, like we model the background carefully using our random box algorithm technique. And then we performed the PSA modeling part, and finally we identified sources in the field, which are shown here is in the far UV magnitude distribution and the near UV. So in both the bands, we kind of reach around 27 magnitude 3 sigma completeness. And this is the source completeness test, like we go around up to 26.5, the 50% completeness for these filters. These catalogs are now in the public domain. We have provided 3 catalogs, far UV sources, near UV sources, and 1 catalog for HST cross-match sources of their UV magnitudes. Yeah, so following that catalog, we started using that, and along with other images we have in the archive to do some more science. So the first thing we started exploring is the UV continuum slope. As we know, like this is blue spectra is the model spectra, and when you introduce extinction to this model spectra, you see there is this change in the slope of this continuum, and that is maximum affected in the UV range because of the high extinction affects the UV photons maximum. So we tried like taking this point, like there is a connection between the continuum slope and how much extinction you have, and to address the extinction part at a particular redshift which was not explored earlier because of the lack of high quality near UV imaging. So this is the redshift range we targeted, 0.4 to 0.75, because of the filter system we have and the definition of Calcity wavelength range. We constrain source selection by not selecting any source which is blended in the UV-AT image, and that we, as a reference, we took the HST image for that. And finally, we have 465 galaxies between this redshift range in this field. And after measuring their beta value, which is the UV continuum slope, we found this distribution. So as a function of redshift within the window we are studying, we don't see any significant evolution. The red error bar shows the 1 sigma scatter of this measurement. So these are the measurements we have. So this value, which was not earlier reported like within this redshift range, because the NUV image is helping us to probe this particular range with more number of source and less confusion. And this is the kind of value we are getting. When we place this, our measurement in the global relation, beta Z relation, these are measurements from all other studies or different telescopes, mostly the HST. So if you see like this cosmic beta Z relation is kind of supported in our measurement, we we see the gradual reddening of the continuum with redshift. For a particular luminosity range, we still see the trend here with our measurement. Now in the other relation like beta and the UV continuum, sorry, UV absolute magnitude, there are different studies talk about this relation. Some find as there is a relation with more luminous galaxies are more redder, but in our cases, like we don't see any specific trend, which is also reported by some other people, but there is a slight trend of the fainter galaxies to show little like radar continuum slope here. Yeah. So we are following up this work with beta IRX relation. Like as I said, like we have the beta measurement from this combination of data like UVAT, HST, and Capino U band. Another thing we have like the Husserl imaging photometric data, and we just combine these two to measure the IRX value, which is the ratio of the layer and LUV, and placed them in this plot with reference to other known beta IRX relations. So this is where our distribution is falling. And we see a kind of SMC-like trend with a large scatter in our distribution. So what further we did, like as we have this other HST photometry for and Switzer band photometry, we took them and did the Siegel ACD modeling. So there are galaxies where we don't have any Herschel detection. So they are not detected in the IR band. So for them, we took up to this band, and then we did the ACD modeling along with the samples where we have Herschel detection. And these are the typical ACD we fitted. And finally, we have the beta IRX measurement for all the samples we have within this redshift range, and this is how they are distributed. The color bar shows the modified Cal-GT delta slope, where we can clearly see the galaxies which are following the SMC like beta IRX relation. They have a much steeper extinction law, and the other galaxies which are having like more shallower delta values, you can see they are following the Cal-GT law, which is expected. Now, we also found a kind of slight trend of massive galaxies to have higher IRX value, which says they are more dust rich and emitting higher in the IRX band. But the fainter end, which we don't have completeness because we don't detect all the faint galaxies in the Herschel band, we cannot comment exactly what is happening here. Finally, the topic which we are currently exploring with this 5 deep fields imaging is identifying Lyman continuum leakers at different redshift range. So if I saw this particular spectra, this is from the model. Now, below 912 angstrom, which we know this is the ionizing part of the spectrum, detecting this photon from distant galaxies is very important to understand the reionization process. So we are taking this as a target and trying to identify such leaker at different redshift. And the difficulty we also already know, like the IgM, which changes drastically when you go to the higher redshift. So far, higher than 4, it's very, so we have not found any direct detection of such sources at very high redshift. Now, our first target is to use the far UV filter. So at Z0, the far UV filter is sitting here. When you reaching Z redshift 1, you can see the far UV filter entirely falls within the Lyman continuum range. So any detection, if you detect for any galaxy which is beyond 0.97 redshift, with a good signal to noise detection, you actually are catching the ionizing photon from those galaxies. And same for the near UV filter, beyond 2.29 redshift, we are actually in the ionizing range, and we can sample Lyman continuum leaking galaxies using these two filters at these two different redshift range. So I'm particularly working in this range in the Goods North field. So there are some preliminary results, but I'll not be talking about them because some other studies on the lower redshift range is also coming to the completion. So yeah, so this kind of triggered by the discovery in 2020, where we first detect this Z equals to 1.42 galaxy being a Lyman continuum leaking galaxy, which is which is the first starting point we had, and then now we have multiple deep field imaged by the UVIT, and slowly we are building up with the different ancillary data we have in the archive to first build a potential list of candidates where we can look for these sources, and then we are trying to increase the detection limit of the imaging to reach the limit where you can detect these faint lemon content bleakers. And with a good number, you uh, talk about their properties at the redshift range where they are not detected that very well. Yeah, so yeah, I'll keep this slide of the deep fields here, and then thanks for your attention.